7. So what is Einstein's theory of gravity? So Einstein's theory of gravity is that mass warps space-time and objects follow that warped path. So mass warps space-time and objects follow that warped path. So we did the example of like the tablecloth thing. Okay, and the sun kind of like sinks down in the middle of it. And then the Earth would travel in kind of like a circular path around that. Okay, that's kind of the idea that Einstein came up with. We also follow in this warp path. The reason why we're stuck on Earth is because we're not going fast enough, right? The moon is going fast enough, so it orbits around that divot in space-time. And so I showed you the bowling ball demo where we put the bowling ball in the middle and then the objects went around that. That's the idea, okay? So how is this different than Newton's theory of gravity? So Newton's theory of gravity, in case you've forgotten, Newton said that objects with mass attract one another with a force. From Einstein's perspective, gravity isn't actually a force. Gravity is a warping of space-time which causes objects to follow a warped path, which looks like a circle, for objects going fast enough. Or it just pulls them into the object if they're not going fast enough. Okay? So Newton said that objects with mass are going to attract one another. Einstein basically explained why gravity works. Newton explained what gravity is. So Newton said gravity is a warping of, or is a force of attraction between objects with mass. Einstein said that it's a warping of space-time. Now, it's important to note, Einstein and Newton are both right. So mass, or gravity is a force between objects with mass because that's what we measure and that's what we see. But that doesn't explain why it works. This explains why it works. Hayden, put your phone up. Okay. All right, number 9. So what example shows Einstein's theory to be more complete? So I think I have a video of this one. I think it's this one.
Right.
All right, so here is a little bit of explanation about the difference between the two of these. There we go. So number 9, what's an example that shows Einstein's theory is more complete, and that's gravitational waves. And I'll put the LIGO experiment. So we have proven that this is true. We have proven that this works. We expected that when objects in space collided, they would cause these ripples in space-time, and that is exactly what they do. They create ripples in space-time. Because here's the thing, Newton's theory does not predict that, right? He predicts that the force would change if you change the mass. So if I have two black holes that collide, the mass is now different of that object, it would affect the gravitational force. But he did not predict any changes. Einstein said that that force of collision creates a ripple in space-time that we can measure. And that is exactly what they found. They measured a difference when those waves traveled through the detector. So I like to use this example. The previous video actually touched on it. Um, actually, let me see. I forget this one's in here. So it talked about if something happened to the sun, Newton said it would instantly affect Earth. Einstein said it would take 8 minutes. So gravitational waves travel at the speed of light. They're just energy. There's no mass to them or anything like that. So that means that when light is traveling through space, it takes a certain amount of time. So if the sun were affected, it would take 8 minutes before we noticed. Right? If the sun magically doubled in mass, it would take 8 minutes before Earth's orbit changed. But at that point, a gravitational wave would push through Earth's orbit and change how Earth orbited the sun. Okay? But it wouldn't happen instantly, like Newton thought. So gravitational waves, and that's what transmits the energy of space-time, essentially. Any questions for me on number 9? All right, 2 more on this, and then we'll take a break to work on practice 3. So, number 10. What effect does gravity have on time? So, gravity causes time dilation. Gravity causes time dilation. So time is dilated by objects that are traveling fast because 2 different people measured the time to be different. Okay? 2 different people measured the time to be different. That's actually the same for gravity. People in 2 different gravitational fields will measure the time to be different. So, let's talk about 11. All right. Bear with me. 11 is complicated. Okay, so I'm gonna take my mask down since I'm far enough away, and that way I can enunciate clear, because it's kind of confusing. We want to use an example to explain why this is. Okay? So let's do that. Excuse me. All right. Let's talk about 2 clocks that are spinning on a disk. Here's the center of my disk. It's rotating around this way. I have a clock out here, and I have a clock out near the edge. Okay. We know from previous classes that these objects will not have the same tangential velocity. This object will not be traveling as fast as this object will. And the simple explanation is this object has a shorter circumference, a shorter distance to travel. Since they both travel around in the same amount of time, the outer clock needs to go faster in order to keep up with the shorter clock, the clock that's closer to the center. In order for that to be true, they also have different centripetal accelerations. Okay? The one further out has to have a larger centripetal acceleration to cause it to rotate. Okay? And the reason for that is centripetal acceleration equals mv squared over r. So the object that's going faster will require more centripetal acceleration on it. Okay, so far so good. So far so good. All right, now remember, according to time dilation in special relativity, so for time dilation, okay, objects that travel faster measure a slower time than slower moving objects. Okay? A person on a spaceship traveling very fast measures time slower than a person at rest on Earth. Okay? All right, any questions up to here? Because I'm getting ready to do the quantum leap. Okay? So I want to make sure you're with me up to here, because now I'm going to make a huge jump. And hopefully you won't fall off the ride. Okay? All right. The principle of equivalence says that for non-initial reference frames, you cannot tell whether you are accelerating or at rest acted on by gravity. Okay? So, if this is true for an accelerated reference frame rotating, the object that is further out has a larger acceleration. Therefore, this one should measure a slower time compared to this one. So, if that's true for rotating objects on a disk, where the one with a larger centripetal acceleration has a slower time than the one with the slower, then the same must be true for objects in stronger gravity fields. Okay, again, we're talking about two objects rotating around on the disk. The one that's further out is going faster, and it has a larger acceleration on it to go faster. Therefore, since Einstein said you can't tell the difference between accelerating and gravity, if that is true for accelerating objects, it must be true for gravity objects. So, objects in larger gravity fields will have a slower time because to that person it feels like going faster even though it's not. And because it feels that way, it must measure that way. So, why is it that this happens? Why does gravity cause time dilation? It causes time dilation because the object acts like it's moving fast. Even though it's not, there's nothing you can do to prove it isn't. Okay? And so therefore, objects closer to large gravity sources will have a different time than objects closer to weaker gravity sources. So if you were to measure the time that someone on Pluto measures in a smaller gravity field further out from the sun, that person will measure time very differently than we will. And if you were to go stand on the sun somehow, that would measure time different also. So that's the key idea for this last one. Okay, does anyone have any questions? Because that is a big, confusing topic. Okay. Go ahead and take a look at practice 3 for me now.